Okay, let us continue our discussion. This is the last section in these lectures, in this class. I hope to finish at least one example to discuss how to handle beam problems using series method. Before the break, we introduced how to derive our beam element matrix. Then what next? Here in section 3, I will introduce briefly how to construct the structure series matrix. And then in the next sections, we will use it to solve problems. Structure series matrix, we have some experience before in truss structures. For beam, we follow the same procedures. You can assemble or add up all element matrices together to form the whole structure series matrix according to the code number orders. Depends on how you assign 1, 2, 3, 4, 5, 6 for the structures. The dimension of the structure series matrix is identical to the highest code number. So you can understand the size of big K at the beginning, even though before finding small k. It will look in this way: force equal to stiffness times displacement vector. The formulation quite similar to truss. The K is equal to a sample of all element matrices together. In this case, we have two element matrices. Add them up together according to the code number, according to the positions. Transformation is not necessary because we are having the same coordinate systems. So after constructing the structure series matrix, you can put it into these equations. And then assign the nodal force vector on the left, assign the nodal force vector, nodal displacement vector on the right. Actually, you can see that series method is nothing but just play with these simple equations, right? For truss, for beam, we keep using the same equation in series method. For series method, you just try your best to find out all the information in these equations. Say, for example, find out the structure series matrix, find out the known force vector, find out the known displacement vector, right? Actually, in series method, you just try your best to find out all the known informations, and then use the known information to solve the unknown displacement, unknown reactions. These are actually what we are doing right here. At the beginning, you can put them symbolically: Q1, Q2, Q3, Q4, Q5, Q6. For displacement, D1, D2, D3, and up to D6. Many simple, but some of them, most of them are well divided. Right? Some may be 0, some may be due to the applied loadings, depends on the boundary conditions. So don't be scared by this symbol. Actually, most of them are well divided. Say, for example, in this problem, I think maybe it's more easy to start from the displacement. Displacement normally more easy to identify. D1. What is D1? D1 stands for the displacement. It can be linear, it can be angular, along direction 1. It is rotation. This end is a free end. Free end is free to translate, free to rotate. So direction 1, question mark. 2 is the vertical displacement at the free end. Again, we have no idea at the beginning. 3, this direction is rotation at the first roller support. Again, this is free to rotate. So direction 3 is question mark. 4 and 5 at the fixed end. Fixed end, fixed. That means there's no displacement, no rotation at fixed end. Direction 6, the vertical displacement at the roller support. Normally, we assume that there's no vertical movement unless we specify in the problems. So it seems that 4, 5, 6 are 0. You can use this inspection to fill in the blank, find out the known information, put it into the force displacement relationship. This is so-called DK, right? Known displacement vector. The upper part is unknown displacement, something that you are going to solve. If you know the known displacement vector, then you can immediately understand the dimension, the number for the known force vector. Right? The known displacement involves number 4, 5, 6. That means the known force should appear 1, 2, 3. Known force vector. Then you just take a look on the picture to see what is Q1, Q2, and Q3. What is Q1? The force or the moment along direction 1. I clear the picture a little bit. Direction 1. Direction 1 is talking about the rotations, which means Q1. Q1 stands for the applied moment. Q1 represents the applied moment about direction 1. From this picture, we can see that we have one applied moment along direction 1. But in opposite direction, the moment is clockwise. Clockwise means negative. So minus M. Q2. Q2 talking about the force along the direction 2, the vertical directions. Again, we have one force. We have a force along direction 2, but in negative directions, minus P. Q3 represents the applied moment along direction 3. But in this picture, you can see that there's no any applied moment, right? You cannot see this blue arrow right here. We do not have any applied moment along direction 3. So Q3, 0. By doing this inspection, by doing this mapping, you can easily find out QK, DK. Minus M minus P 0 for known displacement vector, and then 0, 0, 0 for DK, known displacement vector. In this task, you are asked to use the first part to solve unknown displacement, and then, if necessary, find out reactions if required to do so. So you can see that the procedures is quite similar to TRUST, except that we use different Stevens matrix. Solve the matrix equation. Try our best to do so. This is how we can use our structural Stevens matrix to solve our problems. In the following section, section 4, let us have a look some examples how we deal with beam problems. I remember that there are 2 examples right here. Let's see how far we can go today. These are some basic introductions. Suppose you have successfully formulate the force displacement relationship. You can conduct a matrix partitioning to find out which part is useful, which part is useless, find out unknown displacement, and then find out unknown reactions. Okay, same procedures. Here I'm not going to repeat too many times. You have to try your best to find out QK, DK, construct the matrix, find out K1, K2, K11, K12, and so on. Solve for DU and QU. Right. Same things, just like TRUST. Recall this is a displacement method. So we firstly find out displacement and then find out reactions as usual. One thing I want to remind you. After determining all the unknown reactions, if you know all the reactions, actually you can use equilibrium. You can use force equilibrium, moment equilibrium to double check your answer. Right? For the support reactions, you can use equilibrium equations to check the answer. Similarly, you can use equilibrium equations to find out the shear force and moment at different span for different elements. And then it will help you to construct the shear force and moment diagrams of the structures. This is something that I will ask you in the quiz, how to draw shear force and moment diagrams using Stevens method. We have learned how to draw shear and moment diagrams in the past. So here we just use Stevens method as a tool to evaluate the reactions, internal force. But the skill remains the same. You need to know how to draw this kind of diagrams. Otherwise, you can't decide the beam, decide the column. When you read the notes, they give you, when you read the textbook, they give you one extra equations to evaluate the member end force. Member force means the member end force at the two sides of each beam element. So for example, this is element I, beam element I. Then we have shear, we have moment on the left, we have shear moment on the right. You can use the local member force displacement relationship to find out the member end force. It will help you to evaluate the end moments, end shear, end moment of each element. If you know the end shear, end moment of each element, then it will help you a little bit to draw the shear and moment diagrams. But I think it's more straightforward to use equilibrium equation to draw shear and moment diagrams. Stevens method, just like a tool, help you to evaluate the reactions. If you know the reactions, I believe that you can draw the shear and moment diagram efficiently using equilibrium properties. But in case if you want to fully adopt Stevens method, then here give you one extra equation to use. Not compulsory, this one. Now you will know what I mean in the example. Example 1. Suppose we are going to use Stevens method to find out the reactions at the supports. I will go further. I will also draw the shear and moment diagram for this example 1. But firstly, let us evaluate the reactions at support. We have two supports, one pin, one roller sitting on the ground. This structure is under one concentrated force at the right-hand side, the free end, 5 kilonewton. The questions require us to find out reactions. But you know, in Stevens method, we have no choice. We always need to find out unknown displacement first. Otherwise, you cannot find out unknown reactions, QU. For Stevens method, we need to find out displacement first. So although I did not ask you to do so, but according to the procedures, you also need to find out DU, unknown displacements. You can follow the traditional procedures. Firstly, assign the code number, assign 1, 2, 3, 4, 5, 6, and then construct the element matrix, small k. We have two elements, K1, K2, K2, two element matrix, put them together to form the back K. Back K helps us to formulate the force displacement equation, Q equal to KD. Solve it, then you can get DU and QU. Quite systematic. Let's follow the solution together. We have two elements. Element 1, element 2. They have the same length. Same fracture rigidity, same ER. So when you recall our beam element Stevens matrix, the values inside the matrix should be the same because they have the same length, same ER. Different in terms of the code numbers. How to define the code numbers? I think normally we cut this into two elements, right? No one would like to cut to 3 or 4 elements. No one want to make the calculation too complicated, right? Here we use the shortcut, use 2 elements only. Element 1 on the left, element 2 on the right. 2 elements, they have same length. 2 elements, we have 3 nodes. Node 1, node 2, node 3. Each node we have 2 degrees of freedom. 1 vertical, 1 anti-clockwise. Totally we have 6 arrows. From this picture, we can see that we have 6 degrees of freedom. We have totally 6 degrees of freedom, which tells us that the structure Stevens matrix K should be a 6 by 6 matrix. 6 by 6 matrix because we have 6 degrees of freedom. The code number is up to 6. The next question is how to assign number 1. Where should we start to assign our code number? Number 1, number 2, and so on. In the solution, I try to follow the textbook method at the beginning. Textbook suggests us to assign code numbers starting from the positions with unknown displacement. So the next part is where we have unknown displacement. We have 6 arrows, 1, 2, 3, 4, 5, 6. If you cannot directly inspect where to have unknown displacement, then maybe you can consider node by node, each one separately. At the beginning, start from left to right. On the left-hand side, we have 2 arrows, 1 vertical, 1 rotations. This is a pin support. Pin support, normally we have no vertical displacement, pin support. Rotations. 0 is a known value. 0 is a known values. Rotation, this is free to rotate. So the rotation direction is question mark. Unknown rotation, something that we want to evaluate later. Roller support at the middle. Again, we normally do not have any vertical movement at roller support unless we specify in the questions. Rotation, free to rotate. Question mark. The last one, node 3. Node 3, I think, is pretty straightforward because node 3 is a free end cantilever, which means it is free to display, free to rotate. We have 2 question marks at node 3. Question mark, question mark. So in total, we have 4 question marks. 4 question marks. It also tells you the dimension of K11, 4 by 4. Right? We have 4 unknown displacement to be solved in these problems. You can start to assign code numbers starting from any of these question marks. And in the solution, I start to assign 1 from the right, 1, 2, 3, and 4. 1, 2, 3, 4 are used to denote the positions with unknown displacements. Here are assigned from right to left. If you like, you may reverse the order. It doesn't matter. Just keep your diagram consistent throughout your whole calculations. The remaining 2 arrows, 5, 6, okay, 5, 6. So we complete our code number diagrams. In the solution, we would like to use this diagram to formulate our structure sequence matrix. Here, I would like to also construct the known force vector and our known displacement vector, dk, qk, these 2 things. You can do this at the beginning because it just depends on the boundary conditions and the applied loading conditions. D, displacement vector, contains 6 elements, D1 to D6. Some of them are known, some of them are known values. Here you can see that D1 to D4 are known. This is why we assign code numbers starting from this position, right? 1, 2, 3, 4, unknown displacement. The remaining 2, known displacement. D5, D6, unknown displacement. And the pin and roller supports. So this shows you where is dk. Dk 2 by 1 vector correspond to code number 5 and code number 6. If dk contains code number 5, 6, then you can see that qk should contain the remaining code numbers 1, 2, 3, 4. Or you may do in the same way. Firstly, put down the whole displacement vector. Whole force vector Q1 up to Q6, and then fill in the blank, substitute the known values into this vector, and keep the unknown as symbol. Here, Q1 means the force or moment about direction 1. From the picture, there is no any applied moment along direction 1. There is no applied moment along direction 1. So Q1, 0. Q2, 2 means the vertical directions, the force along the direction 2. From the picture, we exactly have 1 direct force along direction 2, but in direct directions, so becomes negative, -5. Q3 stands for the applied moment along direction 3. Again, from the picture, there is no any applied moment. There is no any applied moment along direction 3. So Q3 is 0. Similarly, Q4 is 0 because we do not have any external movement. We do not have any nodal movement along direction 4. So 0. 0, 0, Q3, Q4. Qk is a 4x1 vector with one non-zero number. Okay, you can directly construct Tk, Qk if you're familiar with the boundary conditions. Otherwise, you may, just like what I do here, put down all the symbol and then fill in the blank, find out the corresponding numbers. Then you can evaluate which part is known, which part unknown easily. So our target is to set up the force displacement relationship. It seems that at this moment we have Q, we have D. The next part is to construct K. If you know K, then you can try to solve. You can start to solve the matrix problems, matrix equation. That is step 1. I call that step 1, discretizations and assign code number, find out the known properties, etc. Step 2, formulate the element simplest matrix. We have 2 elements, element 1, element 2. Similarly, you can see that the element simplest matrix share the same property, symmetrical. All simplest matrices are symmetrical, right? Symmetrical with respect to the diagonal line. So this is one shortcut. You don't need to evaluate all 16 terms because symmetrical property. Before doing the calculations, it's good to have a look of the problems. We have 2 elements. They have the same EI. They have the same length. Okay, same EI, same length. So when you use this element simplest matrix, you can see that their values inside should be the same for element 1, element 2. Because they have same EI, same L. The values inside this matrix should be the same for 1 and for element 2. The only difference is the code number order. So actually you can calculate once and then duplicate to the other elements. Just change the code number arrangement a little bit. Element 1, the length L1 is 2 meters. Substitute into our element simplest matrix, then you can get all the values inside. But how to assign the code number? Just like what we did for truss analysis. Firstly, you have to define the member orientations. For beam, we assume that that members pointing from left to right. So the right end is not F, the left end is not N. Near end node and far end node. When you assign the node code number, we start from NY and then NZ, FY, and then FZ. What is NY? NY means not N, Y direction. The corresponding code number is 6. NZ, not N, Z direction. Z directions mean the rotation. 4, 6, 4, 5, 3. Actually, the code number written on your picture, on the code number diagram. Nothing to remember. Just read the code number diagram that's divided by you, and then you can assign the order easily. 6, 4, 5, 3, 6, 4, 5, 3. Later on, it helps you to construct the structure simplest matrix. You have to sort this matrix in ascending order with code number from 1 to 6. Element 2, similarly, element 2 point from left to right. This is not N, this is not F. So the order of the code number should be 5, 3, 2, 1. The values inside are the same because they have the same length. Right? Don't need to calculate again. Same length, same EI. So the value inside should be the same. But they have different code number order. The first one involves 6, 4, 5, 3. The second one, 5, 3, 2, 1. To make the matrix assemble more efficient, maybe you can enlarge your matrix to a 6 by 6 matrix with the sign identical to the structure simplest matrix. So here I put one additional step. I enlarge K1 to 6 by 6 with ascending code number order. We do the same thing for element 2. Enlarge it to 6 by 6 matrix with ascending code number order. Say, for example, this element, the corresponding index is 6, 6, right? Row 6, column 6. It will be located right here, 6, 6. And then this one, row 6, column 4, row 6, column 4 here. You can resort the arrangement easily. You just need to do 1/2 because symmetrical property. You can always use symmetrical. After enlarging K1 and K2, you can do a mapping easily. You can do addition easily, K1 plus K2. If you are good in this simplest method, actually you can also do one step. You can identify which part is useful, which part is useless. Right? If dk is 0, then the useless part will not affect your calculations. Here I add up K1, K2 together. Then we have a structure simplest matrix together with the force and displacement vector. Then we can formulate our force displacement equation in this way. Do a matrix partitioning. You can see where is K11, K12, K21, and K22. As mentioned, you can see here, K12, K22 will not affect your calculation because they always multiplied with 0 number. So column 5, column 6 actually redundant, no use in this problem. Only the first 4 columns are valuable. So if you can visualize this outcome, actually you can ignore column 5 and column 6 in this 2-element matrix to save the times. Use the upper part to solve our unknown displacement. You can convert these 4 equations separately into 4 simultaneous equations, just like what I put down here, 4 simultaneous equations. Solving these 4 simultaneous equations, then you can find out D1, D2, D3, D4. You can do this in this way. Alternatively, you may use matrix inverse. You can use matrix inverse. This is QK. This part is QK. This is K11. This is DU. Right. QK equal to K11 DU. So if you use matrix inverse, you can also find out DU. K11 inverse times QU equal to DU. Depends on which skill you would like to use. Matrix inverse or solving 4 simultaneous equations. Finally, we get the outcomes. I repeat one more time. In the quiz and examination, normally I would test you up to at most 3 unknown displacements. Okay, so this one is a little bit out of the limitation of the quiz and examinations. 4 unknowns we have here. But anyway, you can solve it using Excel. I will show you later how to play with that calculations. And then we have D1, D2, D3, D4. After solving the problems, we have these 4 numbers. It's good to plot the deformation shape of this structure to see how it looks like. Say, for example, here I sketch the deformations after the calculations. D1 talking about the rotation, right? Because 1 is representing the rotations at the right-hand side of the beam elements. Negative means it is under clockwise rotations. Right, clockwise rotations. we use counterclockwise as positive. So if you get a negative values, mean it is clockwise rotations. D2 negative. Negative mean downward. So it seems that it's okay, right? Because this structure is undergo a downward force. We expect that this position, node 3, should undergo something like downward displacement and clockwise rotation. So it seems that our calculation consistent to what we get. Our inspection, right? Our inspection consistent to what we get of the solutions. D3 is negative because it is also under clockwise rotations. D3 negative means clockwise. D4 positive means anti-clockwise. So this is how you can check your answer roughly using maybe 10 seconds. At least you know the direction correct. The number, no choice, you have to do the detailed checking. Once you know all the unknown displacement, you can use this to find out the unknown reactions using the bottom rows of the matrix equations to find out unknown reactions Q5, Q6 here. Use the last two rows to find out unknown reactions. This row times the displacement vector give you Q5, and then the last row times displacement vector give you Q6. Simple matrix multiplication. 10 for Q5, minus 5 for Q6. Put them on the structures graphically. This is the applied loading. This is Q5. Positive mean it's pointing upward. Q6, negative mean it's pointing downward. Actually, this is the answer for this example 1. Example 1, we just asked you to find out the reactions of these structures. But I will go further. If I ask you to draw the shear force and moment diagram for these structures, you need to know how to do it. Okay, I think it's if you know the reactions, I think it's not that difficult to do so. If you know the reactions, just like this picture, then how to draw the shear, how to draw the moment diagrams. For shear force diagram is quite easy, right? The shear force diagram, because we under only concentrated force. If you see a downward concentrated force, then the shear force diagram will firstly have a certain draw, and then nothing, no loading. No loading means we have horizontal line, and then we have a certain jump, horizontal, and then go down, right? To draw the shear force diagram, actually it just takes you, I think, 10 seconds. If you're familiar with the graphical drawing methods. For moment diagram, you can also use your drawing techniques to draw moment diagrams. But for to draw moment diagrams, you have to pay a great attention to the sign. In the past, when we teach how to draw moment diagrams, in structure analysis module, we draw the moment diagram on compression side based on the derivations. But when you learn draw moment diagram in design module, then we will probably draw moment diagram on tension side. Be careful about the definitions. What I mean is that now this is the shear and moment diagrams. What I mean is that when you at the beginning, when you start to learn how to draw moment and shear force diagram, we normally refer to these side conventions for beam. I copied this from I think mechanics material, something like that. Positive moment means a moment making the member under these concave shapes. Positive moments. If you draw this on a diagram, it becomes on the upper side of the beam. So in the past, when you learn how to draw moment diagram, you are drawing moment on the compression side. But when you learn how to draw moment diagram in design module, we normally draw on tension side, not compression side, because it helps you how to define the reinforcement detailing. Right? For RC beam, we draw the moment diagram on tension side. In this module, I have set both. I have set both methods. For design purpose, we draw moment diagram on tension side because we put reinforcement on the tension side only. on the tension side normally. In this module, I have several because I assume that you know how to do analysis, you know how to do design. So I have several methods. But when you read the textbook, they normally draw on convection sign based on the conventional sign conventions. So here I give you one remarks. So when you draw the moment diagram, if you draw in this way, I will also give you full marks as long as the shape remains the same. Okay, you can draw on tension side, you can draw on convection side. Same to me. This picture is drawing on the compression side, right? Because the beam is bending in this direction. We are drawing on the compression side. But actually here I follow the side conventions, conventional side convention. I'm not using the design definitions. How to draw moment diagrams? In the past, you have learned different skills, right? You can make a card and then calculate the moment equation and right? Classical method. But normally we seldom use it unless you are playing with a very complex loading. Normally we use the graphical method, right? Graphical method gives you one easy way because we have one equations, dm dx equal to shear, right? The slope of the moment diagram is equal to the shear force. Here you can see the shear force is constant. Shear force is constant, which means that in the moment diagram, the slope should be a constant. Constant slope. Constant slope means a straight line. The shear force is negative. Negative means the slope is going downward. So that's why you can put this line immediately once you have the shear diagrams. Then what about the values? The values, the values is equal to the area under these shear diagrams. You can calculate the area easily. It is a rectangle. Give me this value. Graphical method. You have learned in mechanics material as well. Optional. In the notes, in the textbook, they give you one equations. This one, I show you again. In the textbook, they give you one equation. This one, to evaluate the member end force. If you have one beam element, you can use this matrix equation to evaluate the force and moment on the left, on the right. That's why in the solution, you can see there are many matrices. Here. But I call this optional because I think without this equation, you can also evaluate the shear and moment of cell, right? How? If you want to know the moment and shear at these positions, what you can do? If you want to know the shear and moment at these cross sections, actually there's no need to use matrix, right? You can make a cut here, draw free body diagrams. And the reaction here is 5. And you make a cut here. That means you can see the shear, you can see the moment. This time you can use moment and shear and force equilibrium to find out V and M of cell. Right? There's no need to use matrix calculations to evaluate the member end force. It's quite time consuming to do so. If you have software, it's okay, but for hand calculation, I think it's quite time consuming to do so. That's why I put this as reference. I think it's more efficient to use method of section, equilibrium to find out shear and moment. But to complete the story, I also give you some example here to see how to use the matrix equations. But not important, right? Not important. Well, I show you one other things. When you go to Moodle topic 2, you can find out our lecture notes for beam analysis. At the same time, you can find out one additional materials Actually, this one is used to introduce how to use Excel to do matrix operations. I believe that this may help you to finish your assignment. In the assignment, I allow you to use some software like Excel to handle some complicated calculations. Excel actually can help you to do matrix addition, subtractions, multiplications, and also help you to find out inverse of matrix. So for some complex problem, Excel becomes your good friends, help you to find out matrix inverse and matrix multiplications. Maybe I use the previous example one to see, to have a look how to do a matrix inverse. Excel. You have to construct the element matrix yourself. Okay, you have to construct the element sequence matrix yourself. I assume that we have the element sequence matrix, and also I assume that we have the overall structure sequence matrix. In the previous example one, we construct the structure sequence matrix together, and then from the structure sequence matrix, you can identify where is K11. Here I directly input K11 into our Excel spreadsheet. I copy from the notes with a minus. This is the K11, K11 matrix that we calculate of the previous example one for beam. Let me double check. It seems okay, right? Then how to find out inverse? In Excel, if you want to do matrix calculation, you have to firstly select the final dimension of the matrix. Okay. After inversing the matrix K11, the dimension remain the same, 4 by 4. You type in the formula. You can find out the command in the note sheet that I gave you before. Okay, the command to inverse matrix in Excel is called M inverse. M stands for matrix, inverse stands for inverse, M inverse. Okay, you firstly highlight the dimension, the final dimensions, and then type in the command M inverse. Inverse what? Highlight the matrix that you're going to consider. Put the paraphrases. Normally, you press enter, right, in Excel. But remember that in Excel, if you want to do matrix operations in Excel, you cannot directly type enter. If you want to do matrix operation in Excel, you have to type 3 keys together. You type Control, Shift, and Enter key. You have to press Control, Shift, and Enter key. 3 things together. You have to type these 3 keys together. Otherwise, if you just type enter, the computer just gives you 1 values, not a matrix. You have to plug in these 3 buttons together. And then you can double check with, I did not give you the matrix inverse. Anyway, Doesn't matter. This help you how to find our matrix inverse immediately. Then how to use it to find out our unknown displacement. We have one equation, right? QK equal to K1 times du. So similarly, if you know the inverse matrix K1, you can change the equation a little bit. Inverse matrix K1 times QK equal to unknown displacement, right? So we know inverse matrix. QK is something that we have at the beginning. Let me copy QK from our PowerPoint. Right, QK. QK. The mod is du. Du equal to inverse matrix K1 times dk. Oh, yeah. Again, if you want to do matrix multiplications in Excel, you have to firstly highlight the dimension of the final product. What is the dimension of du? We are going to use a 4x4 matrix times another 4x1 vector. So 4x4 matrix times 4x1 vector, the final dimension will be 4x1. You can check this the size easily. This operation involves matrix multiplications. How to do matrix multiplication in Excel? Firstly, highlight the final dimensions, and then type in the formula. The command of matrix multiplications is equal to MMULT. MMULT. M stands for matrix. MULT stands for multiplications, matrix multiplications. And then you just provide the two matrices. We put the inverse matrix at the first parameter. We put our QK at the second parameter. And then you press Ctrl-Shift-Enter. Then you can get the unknown displacement. You can double check with the answer. D1, D2, D3, and D4. It seems the value is okay, right? But you have to change EI yourself because Excel does not support symbolic inverse. You just reverse. You just take the inverse of EI, move it in the denominator. So this shows you some skill how you can use Excel to do matrix multiplication, matrix inverse. Excel also support matrix additions. Suppose we have two matrices, 1, 2, 1, 2, 3, 4, 3, 4. If I want to add these two up together, actually Excel can help you to do so. Maybe I call the outcome as C. Similarly, you have to highlight the final dimension of C. C is a 2x2 matrix. For addition, you can use the plus operation. The first matrix plus, you can use the plus symbol. the first matrix plus another matrix, and then you press Control Shift and Enter. Then you can find out the result after additions. Matrix support, Excel support addition, subtractions, multiplications, and matrix inverse. The notes that I gave you, this one, involve those commands that I just mentioned, M inverse, M multiplication. Excel also help you to evaluate transform and determinant. If you need them, then there are two commands for you to do so. Remember to press the 3 keys simultaneously. Normally, I will press Control and Shift first, and then press Enter. This document, if you're interested to use Excel, then maybe you can have a look at this document. Actually, I showed you those important things: how to get inverse matrix, how to do matrix multiplications. This document also shows you one example, some example right here: how to do matrix inverse, how to do matrix multiplications using example. Okay, these are the things that I want to mention today. Today, maybe let me wrap up the contents that we just go through today. Today, we finished topic 1, trust analysis. So you can start to work out the assignment 1, question 1. You know how to play with trust. And then today, we also go through a little bit about beam analysis. You know how to set up the code number for beam element. You know how to how to derive the beam element matrix. No, not this one, this one. You know how to derive the beam matrix. And then I show you one simple example how to use the matrix to solve beam problems. This one, right? You can use the simplest method to find out unknown displacement, find out unknown reactions. Once you know the reactions, you can use it to draw the shear and moment diagrams. Next time, I will continue to discuss example 2 and the remaining sections. Finally, please remember to send me the group list if you have some preferred group members before next lessons. Otherwise, I will help you to form group. These are the things I want to mention today. Thank you for joining this class. If you have no further questions, this becomes the end of this lecture 3. Thank you, everyone.